section of Chapter 6 is the most important section we cover in statistics. I'll say that again. This section is the most important section I can cover with you in a statistics class. So that's why I wanted to make sure today that I get to it. Okay? And I can tell you also, when you guys come back on Thursday, we're going to continue to talk about the material in Section 6 too. The standard normal distribution. Okay? Now, other than the word "the," which of these words up here do you guys understand? We talked about a distribution, right? We've talked about, well, lots of kinds of distribution. We had a frequency distribution was the first thing we talked about. And then most recently, oh yeah, here's that last page. What kind of distribution were you supposed to create? Well, yeah, there's a binomial distribution, and that's an example of a probability distribution, right? Okay, today we're going to have examples of other probability distributions, in particular this important one called the normal distribution. And you guys have had this word in the book already. They've been hinting at it, saying it over and over again. And I told you guys that, what's the picture that goes along with this? The bell curve, right? And again, this is the most important section because the bell curve shows up again and again and again in statistics. And it's not going to be until later in the course that we figure out why it shows up all the time. Okay? But it does. What does standard mean? That's what my job is today, I guess, and Thursday, is to tell you what I mean by the standard normal distribution. So we'll get to that. Okay. Something we have to do first, I'm going to start off class with a problem. And so you guys can read, and you've been very quiet because you've been taking an exam, so I want to give you a chance to talk to somebody. So read the problem and talk to someone about how you might solve it. Okay, anyone want to share any ideas you guys talked about? Scott?
Well, we feel that you need to know the size of the satellite, and then the percentage of land, or percentage of surface that is land.
Scott wants to know. He said me, but what do you really need? All right, he wants to know the size of the satellite, and what else?
Percentage of surface that is land.
Percentage of surface that is land. Does anyone know that? 30%. 30% roughly? You think about 30% of the earth is land, which would mean how much of the earth is water? 70% of the earth is water. I actually don't know that for a fact. I do have some information here that might help us. Let's see. There are approximately 54,225,000 square miles of land. And there are 142,715,000 square miles of water. How do I know this? Yeah, it wasn't here. I found it in this book, in our teacher's version of the textbook. Well, I probably wouldn't be given. I'd probably have to look it up on the internet, you know, or go to a textbook of some kind. Because you're right. If I don't have that information, I can't really solve this problem, right? Now, do I have enough information to solve the problem? Yes? Why? What? Well, now you can do percentages, right? So what do I want to do? Let me get my calculator out. So 26,940,000. So what is that I just computed? Yeah, that's the surface area of the Earth, if these figures are accurate, which I'm trusting our book on this. Okay? And now what do I do? Okay, so I take 54,225,000. That's the square miles of land that there are. And you want me to divide by what? The thing we just had. Now, I can get that answer very quickly by hitting the second key and the negative sign. It says ANS. And that'll just then divide by the answer. Okay, so I'm going to do that. So I got 0.275. What does that mean? So 27.5% of the Earth's surface is land. Fine. Okay. How does that help me answer the question? So Emily's saying that we basically answered the question. You're saying the probability that it'll crash on land is 27.5%. Do you guys agree with that? Yeah. At least some of you do. Some of you aren't so sure. But here's the interesting thing that Emily's saying. She's saying that if you want to compute the probabilities, all you really have to do is compute the areas. There's this correlation. Right? And you notice what's the title of this slide? Area and probability. Areas can give us probabilities in certain situations. Like this one. Notice there's a couple other things that we didn't really highlight. Randomly selected point. What does that mean? We talked about that. Any point on the Earth is equally likely to be hit by this satellite. And so if you took all the... Remember our formula for probability, right? The probability of an event is a fraction. Now what did I used to put? What was the numerator and denominator of that fraction? The size of the event over what? What do you put in the denominator of a probability fraction? Yeah, the size of what we call the sample space. Or another way to say it is, see, it used to be that what we did was, down here we had all possibilities, right? But up here, we only have the possibilities in our event. What's the event that we're measuring the probability about? Well, hitting what? Land. So you really do want to know the size of the land compared to the size of the Earth, and that's how you guys got this. Okay? And that is correct. Okay, that's very, very nice work. But I guess the point is, again, there's this correspondence between area and probability. Now, I suppose I could somehow talk about every possible point it could hit on Earth, right? But that's kind of confusing because how many different points are there on Earth? Yeah, or the mathematical way to say that is, there are infinitely many points, right? Yeah. Infinitely many points. So that's going to be a problem that we can deal with. And the other thing is that when you measure areas, is that discrete or continuous measurement? That's continuous. So we're going to see today, we're going to be moving into the world of continuous probability. Okay? And this area is going to be a key when we do that. density curve is the graph of a continuous probability distribution. Okay? Up till now, things like binomial random variable or a binomial distribution, that's discrete. That's discrete. Most of what we've been doing has been discrete. Now we're going to move into the world of continuous. To be a continuous probability distribution, I need to have a curve that satisfies the following properties. Oh, and by the way, do you guys know what I mean by a curve? Well, it means that we're going to have a graph, okay, and we're going to have some kind of curve on top, right? You know, something like that on the graph. And so you know, your algebra skills are going to come back here. You have to understand some stuff. These axes, remember what these are called? X and Y. Okay, so those come back. All right, now fine, let's move on here. What are the two properties I need? That's funny. Reminds me of a test question. Remember the second last test question? It said if you have a, well, probability distribution, but that one wasn't continuous, it was discrete. What were the two properties we had to satisfy? Well, they're kind of like this one, but a little different. Here they are. So property number one says the total area under the curve must equal 1. Now that's not what had to equal 1 for us. In the discrete case, do you remember what it was that had to equal 1? Yeah, what about the probability of x? If you add up all possible x's, you add up the probability of x, that has to equal 1. Okay? Well, what we're going to say is that the area under the curve has to be 1. We'll see if that makes sense to you. Number 2, every point on the curve must have a vertical height that is 0 or greater. That is, the curve cannot fall below the x-axis. Well, we had something similar in the discrete case. Do you remember what it was? Yeah, p of x had to be greater than 0. Right? And actually, it had to be less than or equal to 1, too. Now, I guess I'm not requiring that here anymore for continuous. I guess I didn't really need it for discrete either. I mean, it's true, but I didn't need it because the only way I'd ever get the probabilities to add up to 1 is if they were all less than 1. So, that's okay. So anyways, we have these two. Oh, and I'm going to point out just for a second. Can I see a show of hands of people that have taken or will take some calculus? Can I ask that? Yeah, I thought there might be a few of you. See, the tricky question is, how do you find an area under a curve? And one answer to that is that you use calculus. You take the integral of p of x dx. But I'm done. That's all I'm going to say. That's how you find areas under the curves, is with a little bit of calculus. Sometimes. The problems we do, we're not going to need that. Now, because the total area under the curve is going to equal 1, we're going to have a correspondence between area and probability, just like the problem we did at the beginning of class. You don't have to write this all down. It's in your book. I just want to go through quickly. Now, this is the first example your book gives of a continuous distribution. And it is not a normal distribution. It's not a bell curve. This is something different. And it's called a uniform distribution. I should make sure to give examples of these. I'll do on the group work on Thursday also. Okay, so what do we need to be a uniform distribution? Well, we need a continuous random variable. random variable is it's something I'm measuring. And continuous, we know what that means. We've discussed that. It has a uniform distribution if its values are spread evenly over the range of probabilities. Classic example. Waiting for a bus. Or waiting for the rapid transit. Let's say waiting for the bus. If the bus comes every 30 minutes. Okay? But how many of you actually look at the bus schedule before you get on the bus? My wife does. She plans her day out. She makes sure that she takes the rapid downtown. She makes sure she gets to the rapid like with 2 minutes to spare. She'll never get there much earlier than that. Okay. Whereas, that's what you call type A, right? Where there's also the type B personality. Type B, you get out of bed, you get dressed, you walk to the bus stop. When it shows up, I get on the bus. Right? So there's type A, there's type B. All right, suppose I'm really type B, and I just show up and I never looked at the schedule. I could ask you this. How long do you think I'm going to have to wait for the bus? No more than 30 minutes. How long do you think I'm going to have to wait? Maybe you guys can talk about that for 30 seconds. What do we think?
Anywhere from 0 to 30 minutes.
I totally agree, anywhere from 0 to 30 minutes. How long do you think I'm going to wait? Can you tell me anything more than that? You think I'll wait 15 minutes? If I waited 10 minutes, would that surprise you?
No.
If I waited 20 minutes, would that surprise you?
No.
If I waited 25 minutes, would that surprise you? Well, if you just saw the bus leave before I got there, it wouldn't surprise you, right? I mean, if we're saying I pay no attention to the schedule, then my waiting time, right, could be anything, like you said, between 0 minutes and 30 minutes, right? Now, this is an interesting question. If I want to draw a distribution, a probability distribution, see, if I pay no attention to the schedule, it's just as likely that I'm going to wait 29 minutes as I'm going to wait 1 minute, right? If I pay no attention to the schedule. And what you do is you draw a curve. In this case, it'd be a straight line. This is going to be x, and this is going to be the probability of x. Kind of like we did when we did in the last chapter, those probability histograms. But the difference is that instead of being a histogram where you have bars, it's going to be a continuous curve. Okay? And since everything is equally likely, well, you put it up this high. Now, how high? What should be the y value of this line? Well, what I need, remember, is I need the area under the curve to equal 1. That's what I need. So that the area under the curve will represent probability. So, how tall should this rectangle be? The answer is 1/30. Do you see that? Why should it be 1/30? Well, because how do you find the area of a rectangle? Length times width, right? And how long is the rectangle? 30 times 1/30th, right? 30 times 1/30th equals 1. So this is an example of what a probability distribution could look like if it's continuous. I'll come back to this problem. I don't want to say much more about it yet. here's the one that the book's going to do. Well, oh, you want me to go back to that problem? Yeah. So the length was the 30, x was minutes, right? It went from 0 to 30. And the probability goes up to 1/30. I guess I really shouldn't say P in that. I should say Y. Yeah, because probability is going to be the area. Area is the probability. I'll show you that.
So why is it 1/30?
Well, because I need it to equal 1. If I made it 2, I'd do 2
So
times
is it
30
like
is
each
60.
minute is a 30th?
No, but the picture from 0 to 30, I guess I need the line to be exactly 1/30th up. That's how high it has to be. I don't want to dwell on this. It's not the most important thing. We'll come back. Maybe I shouldn't have said it that. You know, the example in the book you're going to read about, they're going to talk about voltage. And they're going to say, hey, the voltage here is always between 123 volts and 125 volts. So how long is this rectangle? 2. So notice, how high did they make the rectangle? 1/2, or 0.5. Does that make sense? So that what's the total area of the rectangle? 1/2 times 2, which is 1. Now, in the example in the book, it says they're using area to find probability. What probability? Well, here it is. Find the probability that a randomly selected voltage level is greater than 124.5 volts. That's hard to read. It's easier if you do this. If you write down, let's let X be the voltage. By the way, is voltage continuous or discrete? It's continuous. You could have 124.5 volts. That's not a problem, right? So what we're computing is the probability that X is greater than or equal to what? Well, I guess just strictly greater than. Greater than what? It says greater than.
Oh, greater than
124.5, right? So that's the probability that X is greater than 124. Okay. And so on the picture, they show you that, hey, if you want to know that probability, you compute this stuff in here, this area. And that's what they do. All right. Action. Okay, so here we go. Yesterday, or I should say Tuesday, we talked about a couple things. We talked about the relationship between area and probability. And we said that this is an important idea for a certain kind of distribution. See, when I say a normal distribution, that's a certain kind. It's different than the binomial distribution. Binomial was discrete, but the normal distribution is an example of what kind of distribution? Continuous, right? And we said that, you know, it's a bell curve, right? So we mentioned that in general, if you have a curve on a graph, you can call it a density curve, that's what it's called, or a probability density curve, if it's the graph of a continuous probability distribution, and it has to meet, well, two properties. Remember, these were the properties for the discrete. All the probabilities had to be between 0 and 1. And what does this mean? So what is it saying? Yeah, if you made the chart for the very last question on the short answer, one thing that you better have, and I'm going to check for, is that your probabilities all add up to 1. Because if they don't, then you don't really have a probability distribution, right? So what's the parallel here? The parallel is that the area under the curve has to total up to 1. Because area is going to be probability, just like it was in the meteorite problem. Okay? So that's what we're getting at here. And then this is the parallel to number 2 there. So we went over that last time. Okay. Yeah, there's a correspondence between area and probability. That's why the area has to add up to 1, because probabilities have to add up to 1. Okay. And I did an example, a short example of a uniform distribution, and there's also an example in the book. And on today's group work, in the second half of class, you'll get another example. So I think by the end of that, you'll have an idea, a pretty good idea of what a uniform distribution looks like. That's the easy one, actually. The hard one is the normal distribution, and that's the more important one. It's the one that comes up more often. Yeah, this is the example from the book. I'm going to skip that. Okay. Here we go. This I did not go over at all yet. The game is going to be this. You are going to find probabilities given z-scores. What are z-scores? Didn't we go over that already? Do you know what they are? Okay. It has to do with standard deviations, yeah. That's right. This is the number of standard deviations we are away from what? The mean. Away from the mean. Okay? Now, let me draw a picture for you. What's that? A bell curve, right? A normal distribution is our new way to say it. I'm going to draw the x-axis right here. And I'm going to point out something. I drew the x-axis under the bell curve because the bell curve never touches the x-axis. Okay? It stays above it because it's a probability distribution. And so here's something you may not have known about the bell curve. You can go out this way infinitely, and you can go out that way infinitely, and this blue line keeps going and gets closer and closer to the x-axis. Anyone have a nice algebra name for what that's called? It's called an asymptote. How many have heard that word before? All right, good. So a number of you have. That's called an asymptote. The x-axis is an asymptote here. Okay. If we have what is called a standard, well, let me not do standard yet. First, let me say, can you show me where the mean is on a normal distribution? Well, you might guess it's right in the middle, and you're right. That's the mean. Now, if I go out far enough to where it just starts kind of changing from the slope going this way to the slope starting to curve that way, and I do that in both directions, that far, that is one standard deviation. So a normal distribution looks like that. So I guess if I went that far again, that would be z equals 2. 2 standard deviations. See, when you say a z-score, you're counting how many standard deviations away you are. I guess if I went this way, I might say z equals -1. If I went a little farther, that far again,
z equals negative 2. Right? Please be aware of something. Z-scores are not areas. Right? Z-scores are how far away you are on the x-axis away from the middle, which is the mean. See, in a normal distribution, the mean and median are the same, right there in the middle. Okay. Now, I'll put this last note in red. If we have a standard normal distribution, which is what the title of this section is. And I said, what's standard? I'll have to explain that. If we have a standard normal distribution, then I'm going to write two things. We'll see if make sure you guys know what I'm saying here. If I write this, do you know what that says? The mean is 0. That's right. Mu, the mean, is 0. And so on the picture, that means that right here, that's the y-axis if you want, right? X equals 0. Although a lot of times, when you do a standard normal distribution, we'll just say z instead of x. They use the variable z to tell you this is how many z-scores you are away. Well, z equals 0 would mean that you're not any distance away from the mean, right? So that's the mean. Oh, and one more thing that standard means. Standard normal distribution means that sigma equals 1. What is sigma? That's your standard deviation, right, of a population, or in this case, of a probability distribution. Okay. So those are facts we need to know, but I need to show you how to apply them, and I'll do that on the next slides. This problem, number 38, addresses a question that many of you have had for weeks. But it doesn't quite tell you that it's addressing that question yet. But here's the problem. It says about blank percent of the area under the standard normal distribution curve is between z equals negative 2 and z equals 2. Okay? Now, problems. If you have any of the problems, the very first thing you want to do is you want to draw a sketch. And when I say draw a sketch, what I mean is draw the distribution curve. You might say, is it really that important? I think yes. I think it is. So I want to draw a bell curve, okay? And it doesn't have to be perfect at all. But it gives you an idea of what you're doing. Matter of fact, if I were grading a test or a quiz, again, here's a reason to show your work. I'd want to see this because I know that the student has a better chance of getting the problem right if they know they did the drawing, because that tells you what's going on, right? We're looking for the area between z equals negative 2 and z equals 2. Well, remember, this line is the mean. That's z equals 0, right? So if I move over 1, here's z equals 2. And here's z equals negative 2. And so the area I'm looking for is here. Okay? So I want to compute that area. So let's see. There's a number of ways to do it. Now, of course, they have tables in the back for people that don't have the technology, and you can look up on the table how much area there is. Why do you have to look up on a table? Well, I think I mentioned last time that calculus is used to compute the area under a curve. And some of you maybe even learned that at some point. It turns out you can't even use traditional calculus methods to get the area under these curves. You can basically approximate the area. That's the best you could do. So mathematicians, what they did, because this is such an important statistics topic, is they made tables back before there were calculators. People spent a long time computing what the area actually was. And of course, nowadays, all that's stored on your little machine right there. You just got to know how to get to it. Okay? So let's go to the machine. Take out your TI 83 Plus. Let's see. I'll get mine. There we go. You turn it on, you have a blank screen, right? What you want to do is you want to find the command normal CDF. Normal cumulative density function is what it stands for. Where? Yeah, where? Well, under variables you have this, DISTR for distributions. So we'll hit second variables. And you notice there's normal PDF and normal CDF. What we're going to want to do in area is we're going to want normal CDF. Okay? So I say normal CDF. We give time for people to find that. And then all I'm going to do is I'm going to type -2, comma is above the 7, +2. For me it is, yeah. They put the comma above the 7. It's above the 7. So -2, comma, +2. And when I'm ready, I'll press enter. Yeah, you should close the parentheses. It might keep an error otherwise. I don't know. Let me see. There it is. So the answer that they give me is what? Yeah, it said 0.95 what? Yeah, I'll say 45. I'll round, right? Or 954. 95.4% of the area, I guess I could fill in. Now, why did I say we were interested in knowing that? Well, because remember what Z actually means? What are Z's? Standard deviations. Wasn't there something special about being 2 standard deviations away in either case? If you're more than 2 standard deviations away, we call that unusual. How much of the data is more than 2 standard deviations away from the mean in the normal distribution? See, there's a little bit over here, right? And there's a little bit over here. You guys see that? But if you added that up together, how much is that all together? Less than 5%. That's right. And some of you have been asking me about, in the last chapter, why do they make a big deal about 5% being the rule for usual or unusual? Well, they couldn't explain it yet because they didn't cover this. But once you understand that what you're really doing when you do area under the curve is you're actually measuring a probability, right? So when I say the area is 0.954, by the way, what's the total area under the bell curve, we said? It has to be 1 because it's a probability distribution. So, yeah, that's 95% of the total area is in red here. And that means if you have a problem and you're computing this probability, this is how I would write it. I would say capital P for probability, and we're going to write Z. Z is my random variable. And I want to write it's between -2 and 2. Let's see if you're familiar with this notation. -2 less than Z less than 2. How many have seen that before? Maybe in an algebra class or something? That's just saying Z is between -2 and 2. So we would say it equals 0.954, because that's the area. Okay? Yes? No. For this problem, they told me find the area between -2 and 2. It really depends what they give you, right? Let's do some examples and see how this works. David? Yeah, I'll say it one more time. The probability that Z is between -2 and 2 is 95.4%. Now, what do I mean by Z? Well, right now I'm being very vague. Z doesn't have any units, right? Z is just a random variable. For this normal distribution. When we get to the next section, the applications, which I'll do today, you'll see that what we actually do is we have a random variable X, and we're going to change it to Z. All right, so you'll see how that works. Okay. Problem 34. Let's try. Oh, I'm sorry. Annette, go ahead. You want to use the tables in the back? You can. Then you'd have to add them, because what you're doing in the back of the book, and by the way, I'll just say this briefly. The back of the book would do this. They would tell you how much area is on this side of the curve. That's what the -2 tells you. And then they tell you how much area is on this side of the curve. And then yes, you'd have to add them together. That was the old thing we had to do when we didn't have the technology. But now, a computer's going to give you the score if you ask it the right way. Kate.
Why do you have only 95% of the area if you want the area to equal 1?
Oh, because there's other Z values. Could someone be 3 standard deviations away from the mean? You could. It's unusual, but it could happen. So see how there's this blue area I colored? This curve keeps going on. And how far does it go on? Did I tell you? Forever. You could be 10 standard deviations away from the mean. That would be extremely unusual. Right?
So you'll never, ever have a P value that equals 6.
I guess, yeah. Only if you had to go from -infinity to positive infinity somehow. Then that would be exactly one. Yeah. But what I'm saying is not nonsense. And let me show you what I mean. When we get to these other problems, there's some ideas you're touching upon that we're going to come back to. See, problem 34, what do they ask? Font. Okay, they're saying, okay, you have, they're pretending that you have a thermometer and da-da-da-da-da. Don't worry about that. Let me just tell you this. Let's word it this way. We want to find the probability that Z, the standard random variable, is what? Greater than 3.68. Now, by the way, that's going to be very unlikely. Do you guys understand that? I mean, let me draw the picture again. Here's the bell curve. Here is Z equals 0. Here's Z equals 1. Here's Z equals 2. Oh, I need more of a picture. these are getting ridiculously close to each other, so much that I can't even draw them well, right? That's what an asymptote means. They get closer and closer always. Here's z equals 3. Here's z equals 4. I mean, I said it's unusual to be more than 2 standard deviations away. What we're computing right now is we're computing, see, this probability is going to be the same as the area under the curve from 3.68, which way? To the right. Now, there is some area under the curve there, but it's very little. So much that, I mean, it's ridiculously a low chance of you finding something that is 3.5 standard deviations away, right? 3.68 standard deviations away. It just doesn't happen often. All right, now I'm going to show you. This time we're going to start with a net. Let's suppose I want to use the table. Okay. If I did, I would go to the back of the book, and I would look up 3.68, and it would tell me the area in here between 0 and 3.68. By the way, let's do that problem just for fun. 0 less than z less than 3.68. Let's do that either using the table. I'm going to do it using the calculator. Here, because I can do that pretty quick. I'll type in normal CDF again, so I'm going to hit second entry so it comes back. But I'm going to change these numbers to make it 0, comma, 3.68, close parentheses, enter. Okay, so the probability that z is between 0 and 3.68 is, what was it, 0.4998, right? Let me see that again. Oh no, 4999 if I round. Wow. 4999. This area in here is 0.4999. Now let me ask you guys, how much area is under the entire curve? 1. Let me ask this. How much area is on the positive side to the right of the mean? Half, or 50%, right? So if you want to know the area of the blue, what do you have to do? You subtract. You can say that this will equal 0.5 minus 0.4999. Right? Of course, that's ridiculously unlikely. I'll do it on the calculator. I'll do 0.5 minus my last answer. Yeah, 0.5 is half. I'm subtracting off the red. I know that everything to the right is a half. I'm subtracting off the red, and that'll leave me the blue. And so how much is the blue? Oh, that's ridiculously small. What's this mean when you see E negative 4? It means, yeah, you have to move this decimal point back 4 places. So the actual answer is 0.0001. It's a seal number. So let's see. That's the probability, right? This is way less than 1% of the time that something happens like this. It's 1 chance in 1,000. No, 10,000. 1 chance in 10,000. Look at this problem. Suppose I want to figure out where is the 95th percentile. Now remember what that means. The 95th percentile on the bell curve. What did percentile mean? If I'm in the 95th percentile, that means what? I'm better than 95% of the other data points, right? So we're talking about a z-score here. You're going to be above the mean if you're better than 95%, right? Probably. At least on a bell curve you will be. So what we're really given here is that the area under the curve on this side is 95%. Right? Okay. Now let me take out a marker because it's going to help. Let me split this. Right? If I split that, how much area is in here? That area is 0.45. Who's with me on that? Okay, some people are not. We said the total blue area is what? No, not 1. The total area under the whole curve is 1. But from the red line to the left where they shaded in blue, that's 95, the 95th percentile, right? Here, they drew the picture for you, right? Normally, if you had a problem like this, I said find some percentile, you would draw the picture. Okay? I put down 95th percentile. I know that that means I want 95% of the data to be here, so the area is 95%. Remember, the percents are areas. The probabilities are areas. And now I say, okay, what should z equal? See, this is going backwards. This is where Annette might have an advantage. I'll tell you what, she's going to go, well, why? Because she was looking at the tables in the back. She's going to look in the back of the book, and she's going to try and find a z-score that'll give me the right area. Now, remember what the back of the book does. The back of the book starts at 0 and goes to the z-score, right? So what's she looking for? She's looking for an area of 0.45, or anyone else that's using the table. If you find a probability of 0.45, you might be able to find a z-score. Do you have it, Jeff? I see you looking at it. Yeah, actually, I'll give you the table. Why not? If you can use a calculator, why not give you the table too? The book gave me 0.95. Why are we looking at 0.45? Because the tables only start at 0. They don't start over here. So the table tells you basically this area in here. So if you look at the back on the table, positive z-scores, where do you see 0.45? Anywhere?
You don't. It starts at half.
If you,
That's
yeah,
what you
that's how
just
you have to
said.
know. You have to know how to use the table. That's right. You go down the side until you see 0.4.
See this?
Hold on. Oh, right. Yeah. Here you are. Oh, I'm wrong. I'm wrong. Yeah. Your table's different than I thought it was. Never mind. You don't need the 0.45. I'm wrong. Well, okay. I wasn't looking at the table. Your table picture looks just like this. So it's even easier. Look up 0.95. Where's it say 0.95? Yeah, and they say the z-score is 1.645. Okay, fine. Let's actually do it on the calculator. Okay? So this is where, and you have all the info you need on page 261, the gray box. They tell you how to do it in Minitab, Excel, on the calculator. Okay? I'm sorry, what? Well, let me do it this way. This is easy. This is easier than the table anyways. Okay? If you're given an area and you want to find the probability, okay? The book says you want to press second variables. Now, where is that? You'll find that, again, we want to get to distribution, right? Second variables gives me distribution. Okay? But now we want to choose inverse norm. That's number 3. Okay? Number 2, normal to CDF, goes from a z-scores to the probability. You do this if you have a probability. So if I press inverse norm, okay, and now if I type in my 0.95, it'll give me the z-score. There it is. So the z-score is 1.645. Hey, by the way, I want to repeat the experiment and just show you something. If I do inverse norm, and instead of doing 0.95, what if I did 0.05? Now, I don't want to type the answer yet. Don't type the answer yet. Just think. On the picture, what would I be computing? Well, the red would be at a different place. See, if I had 0.05, that would mean I'm putting my z here, and I don't know what it is, but all I know is that I want 5% of the area to be to the left. Well, areas are always positive, right? So areas are always positive. But you're right, the z-score should be negative, right? If your area is less than 50%, your z-score should be negative. If your area is more than 50%, your z-score should be positive. Does that make sense? All right. So now let's go here. And what do? The inverse. Oh, does anyone think they know what the answer is going to be without me typing it? Let's see if you're right. Does that make sense to you? It's negative 1.645. Why? Well, because the bell curve is symmetric. It's the same on both sides of the dotted line, on both sides of the mean. David.
When you're saying the more than 50%, you mean the area that was covered in blue? Like if there was like an area that was like 0.45.
Then the z-score would be here, yeah. So you're going to have a negative z-score, right? But if it's more than 50%, yeah, that's right. That's what I'm saying. Okay. So we found the 95th percentile. We got through this section pretty well.